Welcome to the course Power System Operation and Control, in which lecture number 9, Control Areas in Power Systems on Modeling of Two-Area Power Systems. In the previous lecture, number 8, we have studied about steady-state analysis for load demand changes. And we also studied about the dynamic response. And then we have incorporated PI controller in making steady state frequency deviation delta F is equal to 0 so that we can maintain frequency F is equal to nominal value, that is 50 Hz. In this lecture, we'll discuss about the control areas that are available in the power systems. So first we have to understand what is the concept of control area. So far, we have studied about only a single turbo generator, which is supplying power to an isolated load. We have studied only one turbine, one generator setup, which is supplying electricity to the isolated system. But now consider a practical case where the real power system is having a number of generating stations and also number of loads. It is possible to divide an extended power system, say for example, national grid. You can call the entire as a national grid into sub areas. Probably you can call it as state electricity boards, in which the generators are tightly coupled together so as to form a coherent group. So coupled together in the sense, all the generators will respond in unison to changes in the load or speed changer settings. And of course, as you know all the generators must be connected in parallel. And most of the times, whatever the generators we are using in all the power plants are AC generators only. So all the AC generators need to be connected in parallel connection. So whenever we want to connect more than one or two number of generators or more than two generators, that two AC generators in parallel, we have to satisfy certain conditions. So those conditions are called as conditions for parallel operation of generators, which we might have studied in AC machines course. So the conditions to be satisfied whenever we want to connect more number of generators in parallel is, the first condition is the phase sequence of all the machines should be same. The phase sequence should be same. And the second condition is the voltage output or voltage rating of all the generators should be same. And the third condition is the frequency also need to be same. Suppose if any of these three conditions is not satisfied before going for parallel operation of generators, then consecutively the circulating currents will increase and it will lead to the damage of the system. So that's why all the generators which are available in the state electricity boards or national grid or in the entire power system, all should respond similarly for any changes in the load or speed changer settings, and all the generators are electrically connected in parallel to each other. So such a coherent area is called one control area, in which the frequency is assumed to be same throughout in static as well as dynamic conditions. That means for any value of load, irrespective of load condition, always the frequency need to be maintained constant, and that should be equal to our nominal frequency. If it is Indian grid, it is 50 Hz, and if it is US grid, it is equal to 60 Hz. So for this case, to develop a suitable control strategy, the control area can be reduced into a single speed governor, a turbo generator, and load system. So all the control strategies, whatever we have discussed so far, they are applicable for an independent control area. So whatever the PI controller or other LFC controllers we have seen in the previous lectures, all those controllers are suitable to apply for independent control areas. But now, whenever we have multiple control areas, there the challenge lies. So the load frequency control with integral controller achieves zero steady state frequency error. That's what we have seen in the previous lecture. And it offers very fast dynamic response, but it exercises no control over the relative loadings of various generating stations in the control area. So whatever the integral controller we have used in the previous lectures, that will take care of only one single isolated area. It cannot show its impact on multiple generators available in multiple generating stations in the control area. So for example, if there is a sudden change in the load, let's say 1% increase in the load occurs, then the load frequency control changes the speed changer settings of the governors of all the generating units of areas, so that these units which are available in multi areas will bring their frequency to a scheduled value, and that action should complete in very few seconds. However, in the process of this change, the loadings of various generating units change in a manner independent of economic loading considerations. So here two things are there. One is load frequency control, another one is economic dispatch control. So the load frequency control will take care of maintaining frequency or controlling the frequency within the specified range, whereas economic dispatch control will take care of minimizing the total cost of generation. So these two things are separately actually. But now, as a power system engineer, we have to address these two things simultaneously so that we can maintain the frequency constant and the operation of power system is also optimum. So this can be possible by incorporating a necessary controlled signal. So that we are going to study in the coming slides. So here you can see a satisfactory solution is achieved by using independent controls for load frequency and also economic dispatch. So while the load frequency control is a very fast acting control, so which can do its job in very few seconds and regulate the system around an operating point, but the economic dispatch controller is a very slow acting control which adjusts the speed changer setting every minute or of a minute in accordance with the command signal generated by central economic dispatch control. So all these things you can visualize by observing this particular picture here. So here you can see this is one unit where one speed changer is there, governor, turbine and one generator is there. So this particular setup is having its local economic dispatch controller or economic dispatch controller or center you can call it as. So it is going to sense what is the actual power output of this generator and it is going to compare with the desired output, and this desired power output value to be received by CEDC, where CEDC is called as Central Economic Dispatch Computer. So for example, if you take our country as an example, as a national grid, in the national grid you might have some state electricity boards. So all the state electricity boards may have these local EDC centers. So these local EDCs will receive the signal from central EDC. So by taking the input from central EDC, the local EDC will generate an error signal that will be given here, which can be compared with the one more important control signal that is generated by using ACE. So where ACE is called as area control error. ACE is called as area control error. So just similar to this one particular area, similarly we also have some other areas. So every area is going to have its individual local ADCs, and all the local ADCs will receive the command signal for PG from central EDC. So all these control areas require the input from ACE. So where the ACE error is given as the input for the PI controller. So that PI controller is going to generate a command signal for all the areas. So now let's discuss about a new concept called as tie line power. So basically a tie line is a transmission line that is going to connect two or more independent power system areas. So these areas may be different regions or different utilities or even different countries. because sometimes there is a requirement to import or export power from one area to another area. Let's say this is one area, maybe you can call it as area 1, and here we have one more area, let's say area 2. So in a real time, in the real scenario, sometimes there may be a requirement of power taking from area 1 to area 2 in this direction, or after some time there may be a requirement of taking power from area 2 to area 1 in this direction. So for that, we need to establish an electrical connection between these two areas by using some transmission lines. So these particular transmission lines which are connecting these two independent power system areas are called as tie line. So in the modern power system, operation is rarely isolated actually. So nowadays we are not going to have the individual isolated areas. Most of the areas are having interconnections. So all the power system individual areas are interconnected by using this tie line to obtain reliability, stability, and to have economic operation and to share the power among so many areas. So reliability means, suppose let's say when there is no sufficient power available in the area 1 to meet its power demand, we can take the power from area 2 so that the continuity of power can be made possible in area 1. So similarly, the situation may arise that in area 2, the generation may become very much less than power demand. Then you can take the power from area 1 and still you can supply power to the loads available in area 2. That's how we can maintain the continuity of supply in area 2. So in both the ways, whenever we integrate multi areas by using this tie line called as transmission lines, we can have this reliability. So when two areas are connected, the power flow can happen from area 1 to area 2 or area 2 to area 1 depending upon the system conditions. So whatever the power is being exchanged between these two areas are called as tie line power. They are called as tie line power. So what is the need for having this interconnected power system actually? So interconnection through tie lines provides several benefits. So the first benefit is load sharing. If one area is experiencing sudden increase in the load, the neighboring area can give that excess power if it is available. So the load sharing can be, the power exchange can be possible if you have this kind of interconnection phenomena. And economic dispatch. So generation can be scheduled economically across areas. So depending upon the requirement of power in each area, you can decide in which area will go for more generation and in which area will go for less generation. So that is possible only when we have interconnection. And you can reduce the reserve requirement. So each area need not maintain large spinning reserve. Suppose out of the two areas, one area may have more spinning reserve, the other area may have less spinning reserve. And we can improve reliability as I explained in the previous slide. If one generator trips in one area, the other areas can help by maintaining supply to the first area. And better frequency regulation. So tie lines can help maintain system frequency very close to nominal value, that is of 50 Hz in Indian grid system or 60 Hz in US grid system. So all these are the advantages we'll get whenever we have interconnection in the power system in the form of tie lines. So tie lines are very much essential to obtain all these benefits. So now let's see what is the basic principle of having this tie line and how this tie line power flow can occur. So power flow between the two areas depends mainly on these three parameters. One is voltage magnitudes. They also depends on reactance of transmission line or tie line and the rotor angle difference between areas. Let's say the control area 1, this is area 1 having voltage V1 at an angle of dou 1. And there is another control area, let's say that is area 2 having voltage magnitude V2 at an angle of dou 2. Now, this is the transmission line connecting these two areas called as tie line. If this is area 1 and this is area 2, the power flow between these two areas can be expressed as T12 is equal to magnitude of V1 and magnitude of V2 divided by X12 into sine of dou 1 minus dou 2, where X12 is nothing but the reactance of this particular transmission line. Of course, here we have neglected the resistance. And dou 1 minus dou 2 is called power angle difference. So here P12 is expressed as modulus V1 modulus V2 whole divided by X12 into sine of dou 1 minus dou 2. If you want to represent this equation graphically, it will be like this. You can take the load angle on x-axis and power on y-axis. This particular equation has a sine term, so the variation will be like this. The variation will be like this. So this is power and it is varying in sinusoidal fashion. So this is 0 angle and this is dou is equal to 180 degrees, and this particular power will become maximum. This will become maximum when dou is equal to 90 degrees. So now the power flow depends on the angle values. Suppose if dou 1 is greater than dou 2, then power flow will take place from area 1 to area 2. And the maximum power transfer will occur when the angle difference will become to 90 degrees. Because as per this equation, P is equal to V1 V2 by X12 sine of dou 1 minus dou 2. So whenever this angle will become 90 degrees, then it will become sine 90 and it becomes 1, and this power will become maximum power. So power flow is mainly controlled by angle difference here. If dou 1 is greater than dou 2, the power is flowing from 1 to 2, control area 1 to control area 2. Suppose if dou 2 is greater than dou 1, the power flow can be made from control area 2 to control area 1. So depending upon your requirement, you can have power transfer between 1 and 2 just by controlling these two angles, load angles dou 1 and dou 2. So for high voltage transmission lines, as I told, the resistance is neglected. That's why here we are having reactance X. So now let's see what is two area load frequency control. So an extended power system can be divided into number of load frequency control areas interconnected by means of transmission lines, where those transmission lines are called as tie lines, as we defined already in the previous slides. So without loss of generality, we shall consider a two area case connected by a single tie line as shown in this picture. The control objective now is to regulate the frequency of each area. That means the frequency need to be maintained constant in area 1, and also it need to be maintained constant in area 2 as well. So simultaneously you have to maintain the frequency constant in both the areas by regulating the tie line power and also by maintaining the inter area power contacts. So whatever the agreements we made to transfer power from one area to another area, that also need to be taken into consideration. So as in the case of frequency, PI controller will be installed so as to give zero steady state error in tie line power flow as compared to the contacted power. So we already know how we can incorporate PI controller in achieving this zero steady state error in the power. So similarly, we can also use that same PI controller to maintain tie line power flow also. So now the two area load frequency control modeling we can do. So just consider an isolated control area in which the incremental power is delta Pg minus delta Pd. So correspondingly, you can have a tie line power that is exchanging from area 1, that is flowing from moving out from area 1 as P tie 1 is equal to V1 V2 by X12 sine of dou 1 minus dou 2. So that particular tie line power can be expressed by using a synchronizing coefficient called as T12, where T12 is V1 V2 by PR1 into X12 cosine of dou 1 minus dou 2. So here PR1 is nothing but rated power capacity of machine 1 available in the control area 1. So now this particular tie line power delta P tie can be expressed in the form of integral as 2 pi T12 integral delta F1 minus integral delta F2, where delta F1 and delta F2 are incremental frequency changes of two areas 1 and 2 respectively. So similarly, the incremental tie line power which is coming out from area 2 can be expressed as delta P tie 2 is equal to 2 pi T21 integral delta F1 dt minus integral delta F2 dt. Again here T21 is nothing but synchronizing coefficient between area 2 and area 1. So this can be expressed in T12 also by using a constant called A12, which can be expressed as PR1 by PR2. So now the incremental power balance equation of area 1 can be written as, which we have seen in the previous lectures by developing mathematical model for single area, that as delta Pg1 minus delta Pd1 is equal to 2h1 by f1 naught d by dt of delta f1 plus b1 into delta f1 plus delta p tie 1. So this is the only one additional term which we are getting when we compare this equation with earlier lectures, because here we have tie line power. So now if you take the Laplace transform for that equation, it will be modified as delta F1 is equal to delta Pg1 minus delta Pd1 minus delta Pt1 of S into Kp1S by 1 plus Tp1S, where the power system gain is expressed as Kps1 here, and the power system time constant is expressed as Tps1 here. And this particular equation can be represented by using this block diagram. And similarly, we can take for control area 2 also, and you can have the similar steps and derive the same kind of tie line power equation as equation 3.9, which can be expressed by using this figure 3.3. So now in the case of isolated control area, ACE is called the change in area frequency, which when used an integral control loop forced the steady state frequency error to 0. So this ACE is called as area control error. So this ACE1 with respect to control area can be expressed as delta P tie 1 plus B1 into delta F, where B1 is called area frequency bias of control area 1. Similarly, the area control error signal for area 2 can be expressed as ACE2 is equal to delta P tie 2 of S plus B2 into delta F2 of S. So now what we can do, once we have obtained these two area control error signals of two cases separately, we can combine those two and make into one single block diagram. So in the previous lectures we saw, and we have developed a mathematical model for, first initially we have developed for speed governor, and then we have developed for turbine, and then we have developed for generator as well as load. So once we have developed a mathematical model individually for these three, we have combined them. We have combined the mathematical models of speed governor, turbine and generator load. Then that is giving single area load frequency control, or that is giving mathematical model for single area. Now, as we have considered two areas in the power system, we have to take the similar kind of one more block diagram. So we need to have two control block diagrams now, and at the same time we have incorporated ACE signals for each and every area. We have incorporated ACE1 and ACE2. So accordingly, By combining two individual block diagrams and by incorporating two control signals, that is ACE1 and ACE2, the complete composite block diagram is given as figure 1.8.16 here. You can see here this particular region of this block diagram is for control area 1, and this particular region of control area is for control area 2. And these two control areas, individual control areas, are interconnected by using a tie line, as we discussed now. So that tie line can be represented by using this section of block diagram. So here, let me revise all the notations here. So the B1 is called bias constant of area 1. R1 is called speed regulation of area 1. And AC1 is called area control error signal of area 1. And as you observe clearly here, the area control error signal is given as input for PA controller. Because our objective is to incorporate PA controller, which will try to bring this area control error to 0, so that this area can maintain frequency equal to 50 Hz. And then this particular block represent the modeling of speed governor and turbine, and then this particular block represent the modeling of generator together with load. So here the output of this PI controller can be expressed by using this equation, so which will give you the command signal for the area 1. So just similar to area 1, right side we have similar blocks for area 2. Here you can see delta PD2 of S is the load demand power available in area 2, just similar to delta PD1, which is nothing but load demand power available in area 1. So here KPS2 by 1 plus TPS2 into S represent the transfer function of power system or generator load model in area 2. And if you observe carefully here, from area 1 the output signal is delta F1 of S, and from area 2 we are getting delta F2 of S. So we are taking difference of these two frequency errors and we are giving to the tie line block. And in area 2 also we have one more PI controller which will take care of minimizing this area control error signal by giving a command signal delta P2 of S. So as a whole, we can summarize that here the two area model block diagram have two independent control area block diagrams along with two PI controllers and with two area control error signals, that is ACE1 and ACE2. So the analysis of this composite block diagram is quite difficult when it comes to in comparison with the previous case, that is single area power system, because here we have multiple inputs and multiple outputs. So maybe you can think this kind of system as multi-input and multi-output systems, MIMO systems. So this lecture can be summarized as we have understood about the control area concept, and then we have discussed about how two independent controllers, that is low frequency control and economic dispatch control, can be made possible by having local EDCs and central EDCs, that is central economic dispatch center or controllers. And we have introduced a concept of tie line and then tie line power. So where the tie line power can be expressed as P is equal to V1 V2 by X12 into sine of dou 1 minus dou 2. And then we have studied about the two area load frequency control by having some mathematical equations and by developing a composite block diagram which will represent two area load frequency control. And between the two control areas, the tie line power exchange can be possible just by controlling the values of dou 1 and dou 2. That's what we have seen. That means suppose if dou 1 is greater than dou 2, we have seen that the power flow can occur between 1 and 2. That means from 1 to 2. Suppose if dou 2 is greater than dou 1, then power flow will occur from 2 to 1. So this completes the mathematical modeling of two area load frequency control. So that's it for this lecture. Thank you all. We'll meet in next lecture.